OOP code in there. Oh my God. So here's the history, and bear with me, it actually has a reason that I tell you this. So the first scripting capability came in with Swift version 3, ages and ages ago. We were all running MS-DOS at that time. It was something like a very simple event handler. You know, they already had the concept of a button, so if someone clicked the button, it kind of like made sense that shit happens. So it would allow you to say, well, jump to this frame or loop the movie or whatever. That was very limited, so in version 4, they decided, oh, we need a full virtual machine. So they already put in a Turing-complete stack machine that has everything you need, like branches, conditional, unconditional subroutines. All the variables on that stack machine were actually strings. So if you had to add 2 numbers, you would actually push 2 strings onto the stack and then say add, and then the machine will try every possible way to convert a string into a integer, so they could add it and then put the string back on the stack. In version 5, they realized that was a very dumb idea. So they actually added typed variables, and since they're added, they also added a constant pool. So it actually, version 5 looks like someone briefly glimpsed into the Java specifications. And they're like, constant pool, types, cool, implement. They also introduced objects and methods, but that was probably the chapter they didn't read to completion, because like in version 6, they fixed all the OOP stuff in version 5, because they now actually allow early initialization, which makes sense for constructors in objects. They also have now the possibility to see if an object is actually an instance of a certain class. And then in version 7, they actually say, well, we need new function definition, and we could actually have object inheritance. And we could actually test whether an object implements a certain other interface. They also discovered exceptions. And mind you, like they bring in version 5, they bring typed variables. In version 7, they actually bring in a opcode that allows typecasting. Version 8 never happened. Version 9 apparently is where they actually had the VM2 figured out, or found a specification of ECMAScript or whatever. And then version 10 is what we all have to deal with today. However, the reason I'm telling you this is, it's all backward compatible. Everything is backward compatible. We still deal with the whole show today. So where would you actually expect a VM1 code in a Swift file? Like, where would you look for it? There's a tag, like the main data containers I mentioned, that is called do action. Now, they call their stuff action code, so yeah, that's where code is. There's also the do init action that I mentioned before, that is for early initialization. But then it bites you into the R's that we're actually talking about an animated graphics format getting code, because the define button to data structure that defines a button actually contains something called the button record to. And no, it doesn't define 2 buttons. It actually means version 2 of that tag type. So it has a button record to, and that can actually carry conditions. What happens when you press the button, release the button, blah, 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 which actually carry the code that's going to be executed once that happens. The same holds true for a tag called placeObject2 or placeObject3, which again don't play 3 objects but are the 3rd attempt in getting the data structure right. They contain something like clip actions. And a clip action is really interesting because it carries code, actually multiple pieces of code, that are executed when the shape that you defined is currently being obscured by another shape. Makes it very, very predictable how the code is going to be executed. Many tools that we have looked at actually turn out to only handle do init action and do action, even security tools. So you can easily have a shitload of code in a flash file and those tools wouldn't notice. So what is this code? The VM1 bytecode is a variable length instruction set. If you speak Intel, that's what you usually face. It is either a 1-byte instruction that doesn't do anything except for the instruction, or it's an n-byte instruction that comes with a length field. So, mind you, if, bold assumption, a virtual machine will actually validate the code it loads before executing, given this information, it would always know what bytecode follows which other bytecode. So you would have an addressing that will actually go onto the instruction. But no, branches in the AVM1 are actually byte offsets. And they're assigned 16-bit integers to jump into a certain piece of other code. People with experience in code obfuscation and reverse engineering already know where that leads to. Now, the weirdest thing I ever seen in any virtual machine is this. The AVM1 actually has function declarations as a bytecode. So to declare a function, you're not actually like putting it into the file format or something. You have an actual virtual CPU instruction that says the next 600 bytes are going to be a function. That is smart. They can be nested. You know, my idea with this whole function thing is, back in the days at Macromedia, they probably had like free fridges with psychedelic drugs. And then, you know, that one guy realized, oh, the virtual machine actually needs functions, but like the guy that does the Swift file format took those mushrooms yesterday, and he's still tripping on them, so I can't talk to him. And he checked out the code, so I just put it into the virtual machine or something. And actually, like, the good thing is if you standardize the mistake once, you can call it a standard. So when they introduced exceptions and try-catch finally blocks, they actually used the same method. So there's some obvious weaknesses coming out of this. Like, the byte branch offset obviously means that you can easily jump in the middle of someone else's instruction. You can also actually jump out of the code block, so you can easily, and that is commonly used in exploits, jump into an image or an MP3 that was part of your Flash movie. It also prevents large basic blocks. Now, I was really puzzled, and I'm like, okay, so how do they actually make jumps over more than 32K? Because they don't have a representation for that. But, well, I had Adobe CS2 Flash, which is version 10 of their Flash compiler. So, you know, take their compiler, make an if statement, make a big body in the if statement, and tell it to compile. It didn't complain, it didn't warn, it didn't do anything. It produced code that was invalid. So it will actually validate the condition and then jump as far as it could and execute half of the if body as well. The length field on those instructions also have this brilliant property. They allow you to hide data. Because if your instruction actually has a 16-bit argument, it is really easy in the length field to say my instruction is 22 bytes long, which leaves you with 20 bytes for crap. And sometimes you also have an argument array, so you not only have a length field, but then you have a field that says how many arguments come, which can possibly say 0 and then stuff a whole bunch of stuff back to that. Also, as I mentioned, with the clipping, with the code execution on clipping, the order of code execution is actually very non-deterministic. It really depends on, like, is he seeing the shape currently, or is he not? And I kid you not, the Ganesh guys, like a GNU implementation for Flash, they actually figured out that the code execution depends on how deep on the z-axis the object is that you're actually attaching the code on. So if it's further away from the viewer, the code is actually executed later. Makes all sense in the world. Now, well, they obviously did realize that, because they obviously put out a new entire virtual machine, the AVM2. So the AVM2 specification is actually, yeah, quite decent. It hasn't been updated since 2007, but apparently the open source release of parts of it, which is called Tamarind, is actually Adobe code, and apparently that's exactly what you get in the closed source as well. Now, in the specification, the first thing that I noticed was all the length fields are 30 bits. Everyone who does exploitation probably sees the rationale behind it. So there was one smart spec developer, like the guy who wrote the spec.